All right, so today we're going to look at section 3.3, which is on the factor theorem. So we'll do a little bit with factoring and also the idea of using division to help us factor something. So I'll show you an example with just numbers, how you could use division to help you factor. And then we'll get into doing it with problems like polynomials. All right, so just a couple reminders about what it means for something to be a root or something to be a zero. Okay. If you have a number that is a root or a zero of an equation, that means when you plug it in for x, you get 0 for y. And this statement, the next one, it's a biconditional. You can say it both ways. You could say that if you have a number that is a root, you plug it in and you get 0. Or if you have a number that you plug in and get 0, then that number is a root. Okay, so you can say that statement either forwards or backwards. Another thing it means, I didn't write it down, but it's an x-intercept. Okay, if you find a number that you plug it in and get 0 for y, that's where it crosses the x-axis. Okay, so we're going to use, today we're going to use long division. Tomorrow we'll get into synthetic division. But the idea is we're going to use long division to try to find roots, okay, of polynomials. Okay, let's look at an example with just numbers first. Okay, let's say I wanted you to factor the number 12. Okay, so that means break it up into something times something that gives you 12. And I give you the piece of information that 3 is a factor. How could you use that to figure out the other factor?
You divided 12 by 3.
Yeah. Okay. So if you know that 3 is a factor, that means 3 times something is going to give you 12. Well, in order to solve for the something, you divide each side by 3. So 12 divided by 3 gives you 4. And in that case, notice what the remainder is, 0. So if I tell you in general that a number is a factor, like let's say 6 is a factor of 18, and you divide it, what do you think that always means about the remainder when you divide? If something is a factor. Yeah, Megan?
The remainder is 0.
The remainder is 0. Okay, that's very important as well. If a number is a factor, or in the case of a polynomial, if a term is a factor, that means when you do division, you get 0 as a remainder. If you divide something and you don't get 0 as a remainder, then it's not a factor. So like 5 goes into 12. Okay, it goes in, doesn't go in evenly. Okay, you get a remainder of 2 when you divide 5 into 12. Because there's a remainder, 5 is not a factor of 12. Okay, I know that seems kind of simple, but I'm just doing it with numbers first because then we're going to switch to polynomials. Okay, any questions on the idea? Okay. So we just mentioned this. Okay, if you divide a by b and you get a remainder of 0, then you know b is a factor of a. And it doesn't matter if a and b are just numbers. Again, they can be like polynomials or anything more complicated. So factoring a polynomial, the reason why we want to do it is it makes it very easy to find the roots. Okay, so if I gave you something like this, x squared plus 3x plus 2, and I said, in under 2 seconds, tell me the roots. Okay, it's kind of hard to look at it quickly, but if you write it like this, and now I ask you the same question, tell me the roots very quickly, -1, -2. Okay. Once it's factored, it makes it very, very easy to see. Right? So we can do the same idea with polynomials. Let's say I told you this was a factor. and you couldn't figure out what the other factor was. You couldn't figure out x plus 2. Well, if you take x squared plus 3x plus 2, and you divide by x plus 1, the answer you're going to get is x plus 2. You will get the other factor. Now, in this problem, most people, I think, could use trial and error, or just the factoring process, and figure out it's x plus 2. Yeah, but that's not always so easy to do, especially when you get into polynomials that aren't just quadratic. Maybe we'll get into some that are cubic or higher. Okay. So I'm going to go through the steps for dividing polynomials. The process that's kind of, if you've done it before, which I think you all have, it's kind of hard to explain in just words, but it's a lot easier when you do it. Okay, so what we'll do is, as we go through the steps, we'll kind of do an example at the same time. Okay, can everybody still read that? It's a little small. All right, so first thing, if your dividend, okay, the thing under the division symbol, if that's missing any terms, we want to fill those in as zeros. Okay, we need placeholders for every term from the highest exponent all the way down to the lowest. Okay, so Shauna, am I missing any terms in my dividend there? Yeah, which term am I missing?
X squared.
I'm missing the x squared. Okay, so the first thing I'm going to do is put x minus 3. And I'm just going to rewrite it so it has a 0x squared. So x cubed plus 0x squared minus 8x plus 3. Okay, so that's step 1. Step 2, you're going to divide the first term of the divisor, okay, what I just circled, into the first term of the dividend. And we're going to write the answer right above what I circled. All right. So what, if you're thinking, well, what am I really doing, like the calculation right now? You're figuring this out. You want to know what x cubed divided by x is. Okay, so Jay, and if I do x cubed divided by x, what do I get?
X squared.
X squared. So we're going to put x squared right there. Any questions on that? So that's the first term of the divisor going into the first term of the dividend. Now, you're going to take the answer you just got in step 1, and you're going to multiply it out to each term in the divisor and make sure you put like terms in the same columns. That's what it means by put the result under the appropriate term. We're going to line up like terms. Okay, so let's multiply it back up and see what happens. Dylan, what's x squared times x?
X cubed.
X cubed. I'm going to put it right there. Megan, what's x squared times negative 3?
Negative 3x squared.
Negative 3x squared. Okay, now you can see why we put in the 0 term, because we have an x squared term and we need something to combine it with. So the 0 is just kind of our placeholder. Now, you're going to subtract the columns that we just created. Actually, I think my step number is off a little bit. That's step 3. And the one above it, multiply your answer from step, that's actually 2. Multiply your answer from step 2. All right, so now let's subtract those columns. So what I like to do is put a minus sign and put that in parentheses to remember you're subtracting the whole thing. Okay, Leo, what's x cubed minus x cubed?
0.
0, that's gone. And now we have 0x squared minus 3x squared. Okay, so Julian, what's 0 minus 3?
Would it be 3x?
No, that's only when you multiply.
Okay, so 2.
So what would you put for an answer there? 3x.
3x squared.
3x squared, yep. Okay, so 3x squared. And now we just keep doing the same process over and over. Okay, so we'll repeat that, and I'll tell you when you need to repeat it till. You'll know when you're done. But
Instead of like putting them in parentheses, can you just like switch the signs?
you could, yep, any way you can remember to switch the signs or put it in parentheses, yep. Okay. And now we bring down the next term, which in this case is the 8x. And we're going to repeat this process either until you get a remainder of 0, then you're done, or the degree of your remainder is less than the degree of your divisor. So my divisor is a degree 1. Okay, I didn't have the 1 on the x as an exponent, but if you want to put it there, it's a 1. So we need to keep going until we have something less than a degree 1. Right now we have a degree 2. So we're going to do the process again, and then we're going to get a degree 1. And then we're going to have to do this process one more time. So each time you do it, the degree drops down more and more. Okay, so now let's divide x into 3x squared. So Trevor, divide x into 3x squared. What do you get?
X and 3x squared. 3x.
Yep, 3x. Good. Now we're going to multiply the 3x back out. Okay, so Tessa, what's 3x times x? 3x squared. And then 3x times negative 3. Yep, negative 9x. Now you want to subtract those columns. So switch the signs, put a negative in front, however you can remember to do it. Okay, Rebecca, what's 3x squared minus 3x squared?
Cancels.
Cancels. That should always happen. Okay, if you did everything right, that should always cancel out. And Caleb, what's negative 8x minus 9x?
Just x.
Just x. Now I'm at a degree 1. My divisor is also a degree 1. So I got to go one more step, and this is going to be the last time. And I'm either going to get a remainder of 0, or I'm going to get a number. So now bring down the 3. Okay, and do the process one more time. Okay, so Shauna, how many? What do you get when you divide x by x?
1.
Yeah, you get 1. Okay, so divide that out. Plus 1. And if all you wanted was the quotient, okay, in this problem, you're done. That's the quotient. X squared plus 3x plus 1. Now we're going to keep going to get the remainder. Okay, so multiply the 1 back out. 1 times x. 1 times negative 3. And remember to subtract. So at first you might be like, oh, we're going to get a 0 remainder, but not when you subtract. X's cancel, and what's my remainder? 6. That's my remainder. Okay, so there's a couple ways you can write this. You could write quotient and remainder, okay, separate like that. So quotient is x squared plus 3x plus 1. Remainder, 6. That's one way to write it. Or another way you can write it, you've probably seen this idea when you do like numbers back in elementary school. Let's take 13 divided by 5. Okay, just as an example. What's the quotient when you divide that? About Leo?
2. Wait. With decimals or just one?
Just the quotient part.
Maybe 2.
Yeah, 2. And what's the remainder?
3.
3. So you could say, quotient 2, remainder 3. Or another way you can write it is 2, which is your quotient, plus your remainder, over your divisor. 2 plus 3/5. So we could do the exact same thing with a polynomial. Okay. Just move this down. We can say our quotient plus our remainder over our original divisor, which was it x plus 3? X minus 3. That's another way you can write the answer. Bless you. The advantage of doing it the way in red is that you could graph what's in red. You could graph the original problem, and they should come out the same. Okay, so that way you could check your answer. All right, so on your calculator, you'd have to use parentheses around the entire numerator and denominator, but you could check it. So any questions on writing that either way? That's it. That's basically long division. So now if I asked you, is x minus 3 a factor of x cubed minus 8x plus 3? What would you say? Jane?
No.
No, how come?
Because it comes out with a remainder.
It comes out with a remainder. It comes out with a remainder, it's not a factor. All right, let's try another long division one. Okay, Tanya, is my dividend all set, or am I missing any terms?
Looks good.
Yeah, looks good. We've got every exponent from 4 all the way down to the constant. Okay. So, first term of divisor, that's the one you're always using. Divide it into first term of your dividend. All right, so Dylan, what's 2x to the 4th? And if we need 2 off to the side, we can write it down. Divided by 2x squared.
X squared.
X squared. Yep, so we get x squared. Jay, and if I multiply it back out, what's x squared times 2x squared?
2x to the 4th.
2x to the 4th. What's x squared times x negative? What's x squared times x?
Oh, x to the third.
X to the 3rd, again, making sure we put it in the right column. And then x squared times 1 gives me x squared. And Leo, what am I going to do now with all those numbers in the columns?
Subtract.
Subtract. Yep. 2x to the 4th minus 2x to the 4th is gone. Negative x cubed minus x cubed. Sam, what's that going to be?
2x cubed.
Careful. Not
Oh, negative 2.
negative 2x cubed. Unfortunately, this is the kind of process, if you mess up one sign, then the whole thing comes out wrong. But negative x cubed minus x cubed is minus 2x cubed. And then 0 minus x squared is minus x squared. Great. Now bring down your next term. Okay, now we'll do it again. So now the next step, we've got negative 2x cubed divided by 2x squared. Trevor, what's that going to come out to?
X. Negative x.
Negative x, yep, the 2's cancel. And here's where you subtract your exponents when you divide, and then you have the negative left over. So negative x, let's multiply it out. Negative x times 2x squared. Negative x times positive x, which actually that's going to work out really nice in a second. And then negative x times 1, negative x, and subtract. What's going to happen when I subtract here? Yeah, Liam?
The negative 2x cubed and the negative x squared can cancel out.
Yeah, those both are going to cancel. So what we just did is now we eliminated having to do this a whole nother time because 2 terms canceled at the same time. And what am I left with, Leo?
Negative x.
Careful.
Positive x.
Positive x, yeah. Okay. Any question on that? Anything else I'm left with? So that's what we're left with from the calculation, but I also have to do one more thing. Yep. Bring down the -2. Now, can I divide 2x squared into x? No, because that exponent is bigger than that exponent. So now you're done. So your remainder is x minus 2. So quotient is x squared minus x, remainder x minus 2. Or you can write it as quotient plus your remainder over your divisor, 2x squared plus x plus 1. And again, if you did everything right, you should be able to graph the original problem, and they should come out exactly the same. Does anybody want me to show that once, just to show how that would work? Yep, okay. So let's take a quick look at graphing one. All right, so type in the original problem, okay, but make sure you do it in parentheses. All right, so 2x to the 4th minus x cubed. I don't need to put plus 0x squared or plus 0x, bless you, thank you, just for the purposes of dividing. And then we're dividing by 2x squared plus x plus 1. 2x squared plus x plus 1. Okay, so there's the original problem. And now let's type in what we think the answer is. All right, so we've got, in parentheses, x squared minus x plus, let's see, I'm going to try x minus 2, and then divided by 2x squared plus x plus 1. Close the parenthesis for my denominator. Close it for that entire fraction. And I think we're okay. Let's go second table. What I'm doing is I'm just trying a couple values. And can you see how they're coming out the same? I'm probably good. There's really no reason I even have to hit graph if they come out exactly the same. But if you want to see it, we can just hit graph. And the one thing that's nice about checking it on the table is you don't have to mess around with the window. So if this was off the screen somewhere, wouldn't matter. But we can see that's the original. And coming up in red should be the one we did. And they look the same. So that suggests that we probably did it correctly. Doesn't prove it, but it's likely we did. All right, so this kind of seems a little confusing, but I'm going to show you this with numbers, and I think it'll make perfect sense. All right, so if f of x and h of x are polynomials, then there exists two other polynomials, q of x and r of x, which I'm calling quotient and remainder, such that this formula would be satisfied. Let's look at an example with just numbers. Let's let f of x be the number 13. Let's let h of x be 4. I want to pick something that would have a remainder. So the quotient, what do you get when you divide 13 by 4? What's your quotient? Juliana? 3. Quotient would be 3. And what's your remainder? 1. So let's just plug those numbers into this formula, and I'm going to show you that it works. 13, hopefully, is going to equal 4 times my quotient plus my remainder. Is that true? Yeah. That's kind of another way you can check your answer. Like if you did a long division problem, that's how you would check it. Take your denominator, multiply by your quotient, add your remainder. If you get the original numerator, then you did it right. Okay. This would work exactly the same with polynomials. Take your denominator, multiply by your quotient, and then add your remainder. If you type that into y1, and then you type your original numerator into y2, those would also look the same. Okay, so it's just kind of like what we just did, but it's just a different way to think about it. That's all. Okay, remember that when we're dividing, the degree of your remainder always has to be less than the degree of your divisor, or the remainder comes out 0. That's how you know when to stop. All right, so if you have a problem where you are dividing by something linear, okay, that means that this part right here is like just x plus 1, or x minus 3, y minus 7, okay, something like that. If you divide by something linear, what's 1 degree less than linear? Kind of like what's a step down from a linear equation? Like a step up would be a quadratic. What would be one step down?
A constant.
A constant. So when you divide by a linear polynomial, if the remainder has to be a lower degree, the only lower degree than linear is just a constant, just a number. So anytime you divide by something linear, your remainder will always be just a number. Okay, so I'm going to show you something that's kind of going to give us a hint at the next thing, which is how can you find the remainder? Okay, this is actually going to be called the remainder theorem, without actually doing the whole problem. What if that's all you wanted to know? Just the remainder. And we've talked a little bit about why you might want to know the remainder, right? What might be handy if you know the remainder? What did we say that tells you? Remember, if the remainder comes out to something special, then, yep.
Then it'll tell you if the divisor is a factor or not.
Right, it's going to tell you if what you're dividing by is a factor. If your remainder comes out to what? 0. So it'd be very handy if we just had a quick way to find the remainder, and we do. So let's say we take a polynomial, f of x, and we divide by h of x. Specifically, h of x is going to be something linear. X minus 3, or it could be x minus minus 2, so it could be like x plus 2. But the point is it's dividing by something linear. Okay. Using the formula that we just had, if I can try to get them both on at the same time. Okay. Using the formula we just had, numerator, right? Numerator equals what you divided by. What I divided by is x minus c times your quotient plus your remainder. So all I really did was plug into the formula I had up above specifically for what I'm dividing by, x minus c. And we already said the remainder is going to be a number. Okay, we already know that because we divided by something linear. So now, I want you to see what happens if you make this substitution. Okay, let x equal c. Okay, so what I'm going to find is f of c. Okay, and I'm going to plug it into that formula and watch what happens. If I plug c in, into my original function, because that's what that means to do. Plug c into your original function. And let's look what happens right there. You end up with c minus c, and then in parentheses, q of c plus r. Well, what's c minus c? 0. And what's 0 times my quotient evaluated at c? 0. So I get f of c equals r. So what does that mean? If I plug the number c into my function, the original function, okay, whatever you divided by, if you plug c into your original function, what's the result? What does it say? Yeah. The remainder. So we have a shortcut for finding the remainder. All you have to do, if you're dividing by x minus c, is take the number after the minus sign, plug it into your original function, and that will just tell you the remainder. And that's the remainder theorem. Okay, so the remainder theorem says that if you take a polynomial and you have to divide by something linear, okay, the way I taught it to you, it doesn't work for like x squared minus 5. It's got to be like x minus 5 or x plus 7. But if you divide by something linear, take what comes after the minus sign, plug it into your numerator, and that just happens to give you the remainder. The reason why I tried to just go through with the formula. Now, if you want the quotient, there is no quick way to do that unless you know synthetic division. But there is a quick way to get your remainder. Okay, so let's find the remainder. We're going to do a couple problems. Let's start when we divide f of x by h of x. Okay, so let's, looking at h of x, J-N, what's the number after the minus sign? 3. 3. So what do we do with the number 3 to find my remainder?
Would you just subtract it from? I'm not sure.
Anyone help him out? What does the remainder theorem say to do? We're dividing that. We're dividing. I'm not going to write it all out. I'll just put f of x divided by h of x. We're not actually going to figure it out. We're just going to find the remainder. So what do we do? Yeah, Rebecca?
Use 3
Mm-hmm.
as like the C in the last column.
Okay, so 3 is going to be c, and where does that get plugged into?
Where the X is.
In which function?
F.
Yes, in function f. So to find your remainder, do that calculation out. F of 3. If you can do that out, that's your remainder. So we're going to get 3 cubed, which is 27. 3 squared gives me 9 times 2.
18.
Minus 18. Plus 3. Minus 5. All right, so we get 27 minus 18 plus 3 minus 5. Okay, so we get 7. Okay. So if you were to actually do out all the long division, you would get a remainder of 7. Yeah, did I make a mistake?
Should it be negative because x minus 3?
Oh, no, you plug in the number after the minus sign. We're going to get to that point with the next one. You have to be very careful about the sign. But it's always the number that comes after the minus. Okay, but yes, that is important for the next one. Okay, so in and of itself, the remainder 7 is not really important. But what does that tell you? That the remainder came out to 7. What do you know? Yeah?
There's no factor.
H of x is not a factor of f of x. Correct. Okay, so now let's do f of x divided by g of x. And again, we're just going to find the remainder. So, what would I plug into my numerator to find the remainder with f of x divided by g of x? Megan?
Would it be negative 1?
Yes, you've got to think of g of x like this. Okay? It's the number after the minus sign. Okay, so it's very important we get that right. So now you're going to plug negative 1 into f of x, and that'll tell you the remainder. Right, negative 1 cubed gives me negative 1. Negative 1 squared is 1 times 2 is 2. Then minus 1 minus 5. Right, so we get negative 1 minus 2 gives me negative 3 minus 1, and then minus 5. Negative 9. Okay, so again, remainder is negative 9. Not super interesting, but it does tell us something important, that g of x is not a factor of f of x. Okay, any questions on that one? So come in really handy if I gave you a really large problem. Like let's say I gave you something with an exponent in the double digits, like x to the 35th minus 2x to the 12th plus 7. Find the remainder. You don't want to write out all the zeros for every term you're missing from the 32nd exponent all the way down. Okay? And then try to do the division. Just use the remainder theorem and it's a lot easier. Okay, a lot of people on the test, they try to do it with the zeros, but they usually make a mistake. And I give you some insanely high number. Okay? It's something that the remainder theorem would really speed up. All right. So, kind of going back to that formula that we came up with, this f of x equals your denominator times your quotient plus your remainder. So, if you divide by x minus c, okay, then this is what the remainder theorem tells us. Your numerator equals your denominator times your quotient plus your remainder. But instead of writing r for remainder, I put down the formula for the remainder. All you do is take the number that comes after the minus sign, plug it into your original function, and this calculation is what we just did in the last 2 pages. That's the remainder. All right, so now let's suppose that c is a root. What does that mean if something is a root? You plug it in for x and you get what for y? You get 0. So if c is a root, then you guys just told me that means you plug it in for x and you get 0. That's the result. So if that number happened to be a root, then the answer would come out to 0. So now your formula turns into this. Your numerator equals your divisor times your quotient plus your remainder. But if you do it with a root, your remainder is always 0. We've already kind of mentioned that idea. I'm just trying to tie it together one more time. And this leads us to what we call the factor theorem. Okay, so the factor theorem says that if f of x is a polynomial, and it's a biconditional statement. So actually, I'll read it both ways. If x minus c is a factor of f of x, then c is a root. Or I could say if c is a root, then x minus c is a factor. So now if I gave you a polynomial and I said to you x minus 2 is a factor of my polynomial, then what that means is 2 is a root, or 2 is a 0. So we can kind of look at that statement both ways. If you know something's a factor, then you automatically know the root. If you know the root, then you automatically know the factor. Okay, and I'll show you in a second where we could apply that problem. We could do it in a problem like I could say to you, write down a polynomial, write down a parabola that crosses the x-axis at 3 and 7. So I'm telling you the roots, 3 and 7. And if you know the two roots, the two values for c, 3 and 7, then you should be able to figure out the two factors. Just x minus the numbers I just said. Okay, so we'll maybe we'll try one like that after. All right, so this says to use the factor theorem to show that x plus 2 is a factor. So what does that mean we really need to do? Rather than do out the whole division, we just have to hope that when you divide these two things, you get a remainder of what? 0. That idea that J.N. just said, that's the factor theorem. If you get a remainder of 0, then you must have a factor. So, let's call the bottom one h of x. Let's call this one f of x. So when we divide f of x by h of x, okay, the remainder that we're going to get, can somebody tell me how I would do the calculation to find the remainder? Yeah, Rebecca.
Substitute -2 in for the x's after x.
Perfect. Plug in -2 into f of x and hope you get a remainder of 0, and then you'll have done what they wanted you to do. So Sam, what's -2 cubed?
-8.
Yep. -8. And Shauna, -2 squared? Times 5? 20. How about Caleb? 5 times -2?
-10.
And -2. -8 plus 20, that's going to give me positive 12. 12 minus 10 is going to give me 2. 2 minus 2 gives me 0. So, does that mean h of x is a factor? Yes, because it divides in without remainder. Now, if you wanted to know the other factor, then you do the long division. Okay? Because now you should be able to factor that. Okay? Knowing that x plus 2 is a factor, this equals x plus 2 times something. How do you find the something? Divide each side by x plus 2. And that's what we did in the first part of today. That's the long division. When you do the long division, your quotient would be what degree here? If you divide what I underlined in red by x plus 2. Oh, yeah, Megan?
Second degree.
Yeah, it would be a quadratic. Because if you multiply a quadratic by something linear, that turns it into a cubic. All right, so if you do out your long division, look at your quotient. That's what would go right there. That's the something. It's the quotient. So now this kind of gives you an idea of how you could solve higher order problems. If you can take something that's a cubic and you know something is a factor, you can divide through by it and turn your problem into a quadratic, and then we can solve it with quadratic formula. So that's always the goal, to eventually turn it into a quadratic. How would you know x plus 2 is a root to start with, though, if they didn't tell you that? That's a little trickier. We'll talk more about that later. All right, so we've said a lot of different things about roots and zeros and x-intercepts and factors and remainders. So I'm just going to kind of mention all those ideas here and show you that they're equivalent. Okay, so if c is a root or a zero, that means when you plug it into the equation f of x, the answer you get is 0. It also means that you could say that that number is a 0 of the equation. It's kind of the same as the first one, but it's worded a little different. The second and the third one really are exactly the same thing, just using a synonym, really. But this fourth one is the one that's important. If c is a root, x minus c is a factor. Right? So if c is a 0, or if c is a root, then you know that x minus the root is a factor. And if you want to think graphically, it means that the point c comma 0 is an x-intercept. Okay, so all those statements are equivalent. Probably the most important one to understand is the fourth one. Hey, any questions on any of those 5 different statements? Okay. So, here's a problem like I had told you before. I want you to find a polynomial of degree 3. The coefficients have to be real numbers, okay? So, in other words, I don't want you to do anything with I. No imaginary stuff. And I want the roots to be -2, 1, and 3. Okay, so -2, 1, and 3, those are like your c values. You have 3 of them. So let's start with -2. If you know -2 is a root of f of x, okay? F of x is the goal. What is f of x in this problem? If you know -2 is a 0, can somebody tell me something else you would know? Yep?
X plus 2 is a factor.
Perfect. If -2 is a root, x minus -2 has to be one of the factors. What about if 1 is a 0 of our polynomial? What else do we know? If 1 is a 0. Yeah? X minus 1 is another factor. And lastly, if 3 is a 0 of f of x, x minus 3 is a factor. Okay, so now let's just multiply that out. So we get x squared minus x plus 2. Gives me -x plus 2 is 1, and then -2. And distribute out one more time. X cubed plus x squared minus 2x minus 3x squared minus 3x plus 6. And combine like terms. X cubed, x squared and -3x squared is how much? Yep. 2x squared, -2x minus 3x minus 5x plus 6. So, if I graph that on the calculator, which I will, where should it cross the x-axis? Because we built, or we like created that polynomial and forced it to cross at certain places. Caleb?
The -2, 1, and 3.
It should cross exactly at -2, 1, and 3. So let's try it. So we have x cubed minus 2x squared minus 5x plus 6. Zoom 6 should work to see the roots. It might go off the screen, but you'll definitely be able to see the roots. There's -2, 1, 3. Crosses exactly in the 3 numbers that we want. Any question on that one? Come back to that in a second. Something similar to this one. What if I asked you to find a quadratic, so a degree 2, and I only want it to cross the x-axis at 4? How would you find a degree 2 that only crosses the x-axis in one spot, like 4? Well, if it's a degree 2, how many factors is it going to have? Like when you break it up into parentheses. 2. And I'm telling you that the root is 4. What does that mean the first factor would be? X minus 4. And what does that mean the second factor would be? Yep. X minus 4. So what we just created there is a polynomial with a double root. Okay, we're using the root 4 twice. So now that, if you do that out, you're going to get a parabola, but it's only going to cross the x-axis in one spot. Okay. So you can use the same factor more than once. That's what I'm getting at. And if you wanted to make a cubic that only crossed the x-axis at number 4, there you go. Now it's a cubic, and still only crosses the x-axis in one spot. Okay. All right, so let's see if we can find the zeros of this. Now this is a cubic, but it's going to work out nicely when we do factor by grouping. So remember, factor by grouping means take what you can out of the first 2 terms and what you can out of the second 2. If there's nothing in common the way I just said, then you might have to rearrange it. But I think the way it's written, the first 2 terms and the last 2 terms have something in common. Okay, Tessa, if you look at the first 2 terms, what did they have in common?
X.
Yep, x squared. And Rebecca, if you factor out x squared from the first 2 terms, what do you get? X plus 2. Now the whole goal with factor by grouping is that you get an x plus 2 again. That's what we'll hope is going to happen. Actually, let's look at the next 2. Does anybody see what I could factor out of the next 2 terms and hopefully get an x plus 2 after I do it? Yep.
-4.
Yep. If you factor out a -4, you get x plus 2. And now you do factoring again with the 2 things I underlined in black. You're going to factor out from that and from that. So we'll factor out an x plus 2. And if I do that from the first box, what does that leave me with? Megan?
X squared.
X squared. And from the second box? Yeah, the -4. Now we've completely factored the left-hand side. Leo, what do I do with each one of these factors to find the solution?
The x squared minus 4 will be factored again.
Okay, yeah, we could factor it again. I wasn't thinking that. There's a couple ways you could solve it. How does x squared minus 4 factor since it's a difference of 2 squares?
Oh, x squared plus 2 and Or x plus 2, x minus 2.
X plus 2, x minus 2. So now if we solve it, what are the two places where this would cross the x-axis? I mean, it could have been 3, but in this case we have what we call a repeated root. Sam?
2 and negative 2.
2 and negative 2. Which one of those roots is a double root? Negative 2. So what usually happens at a double root, okay, this is a cubic with a positive number in front. So it's going to look something like that. So at a double root, the graph goes, it touches that number and it bounces away from it. It can't cross through it. It just touches it and goes away. So the double root is at negative 2. So the graph is going to have to come up. And because it's a double root, it's just going to touch it. It's going to bounce away from it. And it's going to go back up like that. Okay, so it's going to look something like that. Any questions on that? Same thing with that parabola I showed you earlier with a double root. It would come down, it would just touch the axis, and it would bounce away from it. It can't cross through, because if it did, it can't cross back through at the same spot. It would have to cross through somewhere different, creating another root. All right, so let's try this one. We use a graphing calculator to find the roots. Okay, before I do it, how many roots could this have at most? And we're thinking just real numbers. How many roots could this have at most? Leo? 3? How about at minimum? 1. Right? It's a cubic, which is a continuous. It's a cubic polynomial. It goes up forever. It goes down forever. It's going to cross the x-axis somewhere. But it could have anywhere from 1 to 3 roots. I should be careful how I say that. 1 to 3 distinct roots. It always has 3 roots. It's just some might be repeated. It might not be distinct. Okay, so 2x cubed minus 4x squared plus x minus 2. So I'm not really looking for like local minimums and maximums, so if that goes off the screen, that's okay. Okay. How many roots did I end up with? Yep. 1. So because I only ended up with 1 root, with a cubic, that could mean one of 2 things. The first thing it could mean is that's a triple root. It's like x plus 2, x minus 2, x minus 2, x minus 2. That's one thing it could be. Or the other 2 roots could be imaginaries. It's possible that this problem has 1 real root and 2 imaginary. Okay, we're not really getting into imaginary yet, but we will be. So could be either one of those situations. Right now, we don't know. But one thing to keep in mind is imaginary roots always occur in pairs. So with a degree 3, kind of the different scenarios that could happen between real and imaginary, you couldn't have 0 real and 3 imaginary. First of all, we said cubics always have to cross the x-axis at least once. And you could never have 3 imaginary. That's an odd amount. Imaginaries always occur in pairs. So with a degree 3, you either have that situation. You could never have 0 imaginary. Actually, you could. Yeah, you could have that. But you could never have 1 imaginary. That's impossible. And you could never have 3 imaginary. That's impossible. So it always has to be one of these situations. Okay? And you might be like, oh wait, didn't you just say a real might only cross the x-axis twice? That's that case right there. When I say 3 reals, I don't mean that they're distinct. Maybe they're all 3 the same, all 3 different, 2 the same, 1 different, I don't know. But those would all fall into this case. So one of these two situations is happening. But in this case, they just want us to find the root. So pick a point left. Okay, pick a point right, and do our guess. Okay, so we get x equals 2. That's our root. Okay, so any questions on the three things we looked at? We did the long division, the remainder theorem, and factor theorem. Okay, don't worry too much about the real and imaginaries. That's not coming up more until later in the week. It's not time. All right, so homework for tonight. It's on page 171. 1, 2, 4 through 6. I think I can simplify this a little bit. 9, I erased one of them, so now it's just 9 through 21 odd, I think. Yeah, just 9 through 21 odd. So 1, 2, 4 through 6, 9 through 21 odd, 25, 27, 32.